Hello everyone, welcome to today's Polariton webinar. My name is Oliver Sun, and I am an undergraduate student at Joel Yandros Group at UC San Diego. Today, I'll be your host for this Polariton chemistry webinar, along with Stefan Wanden Wilbanger, who is a postdoc in our group. It is our great pleasure to welcome Professor Finkelstein Shapiro from Universidad Nacional Autónoma de Mexico as today's speaker. Before we start, like usual, we would like to make a few announcements and introduce the mechanisms of this webinar series. Since September, we changed the frequency of the Polariton chemistry webinars. They now happen every month instead of every week. Like before, we will keep sending you emails advertising about the next Polariton chemistry webinars along with the Zoom registration links. If you did not subscribe to our mailing list yet, do not hesitate to do it by following this link. To stimulate exchanges amongst our community, we maintain a Facebook group called Polariton Chemistry Online Community. This group is not only intended for us to share information about the webinars, but it is also meant as a space for you to share your research and ideas. So whether you are particularly excited about one of your latest publications, or if you want to share about a new position that is open in your group, please share it on the Polariton Chemistry Online Community. Also, if you missed one of our webinars, if you want to catch up with some details you missed in the previous sessions, or if you're just very eager to rewatch your favorite talk, please remember that we upload all of the webinars on our YouTube channel named Polariton Chemistry Webinar. If you want to keep up with the webinars every month, please consider hitting the subscribe button there. We are excited to announce that next month, our Polariton Chemistry webinar series will host a roundtable where 4 panelists will discuss and contrast the notion of strong coupling in the collective and single molecule regimes. More details about this roundtable will be presented at the end of today's webinar. Finally, I would like to introduce the mechanisms of the webinar. During the talk, attendees are all muted. For those who have questions, you can click the raise hand button, and I will interrupt the speaker at the appropriate time and enable your audio to ask questions. Also, you can type your comments or ideas using the chat function so that you can share them with everyone. For Q&A, you can type your questions there, which will be addressed at the end of the talk. For the questions that are not answered due to the webinar time limit, we will collect and send them to the speaker after the talk. Now let's move back to today's webinar. It is our great honor to have Professor Daniel Finkelstein Shapiro from the Autonomous Mexico National University as today's speaker. Professor Finkelstein obtained his PhD in 2013 from Northwestern University. After a first postdoctoral experience at Arizona State University, Tempe, Professor Finkelstein moved to Sweden for a second postdoctoral position where he studied coherent 2D spectroscopy, open quantum systems, and bright and dark polariton states. 1 year ago, Professor Finkelstein obtained an investigator position at the National Autonomous University of Mexico, where his line of research articulates around the design and synthesis of functionalized nanoparticles for photochemistry, the exploitation of quantum optics phenomena, and the characterization of these nanomaterials using magnetic resonance and vibrational spectroscopies. He also has interest in the theoretical description of the evolution of photoexcited states in functionalized nanoparticles using toy model theoretical description of multidimensional spectroscopies. Today, he will give a talk entitled Dissipation, Coherence, and Interferences in Polaritonic States of Molecules Strongly Coupled to Plasmonic Nanoparticle. Please join us to welcome Professor Daniel Finkelstein. Professor, you may now share your screen.
Thank you. Is it working? Yes, okay. Thank you, Oliver, for the introduction and also for the invitation, as well to Joel and to Wei. I'm very happy to be able to contribute to these wonderful webinars. And what I want to tell you today is about the photoevolution of excitations of polaritonic states that exist when molecules are adsorbed on nanoparticles. And to set the stage, well, first I will mention that this is a collaboration between 3 universities. So UNAM in Mexico, Lund University, the Department of Chemical Physics, where all the ultra spectroscopy is done, and then in Turkey, who makes the nanoparticles. So to start with, I don't need to explain this specific picture, but what I want to do is emphasize how polaritonic states are different when one is using nanoparticles than when one is using cavities. So if we start with the simplest or the first system with a microwave cavity and an atom Rydberg states, we have essentially this picture and not much more. And so the system is very clean. And then when we go to molecules, which is most of the topics in these webinars, we miniaturize the system. We go from some centimeter-sized cavity to something which is on the order of hundreds of nanometers, maybe a little bit bigger. But we have to pay a price. And the price that we have to pay is that we now have some dark states to contend with. And maybe these dark states don't play a big role, for example, in the linear absorption, but they're absolutely essential whenever for influencing the evolution of the photoexcited state. And if we keep miniaturizing this, so if we confine the cavity mode inside the plasmonic nanoparticle, we have to again pay a price, and the price that we have to pay is that we now have a conduction band that is going to also heavily influence the dynamics. And by and large, what I want to tell you today is how this band influences the excited state dynamics, and then discuss a little bit how this can be useful. Just one slide of overview of the different flavors of plasmons that can be used and that have been used. They all have their advantages. So one can use these maybe open cavities with surface plasmon polaritons that have been studied a lot, also with ultrafast spectroscopy. We can have either bow ties or nanoparticles on surfaces that are very useful for having strong coupling in the single molecule limit. And then we have these nanoparticles that I'm going to be discussing, which are very nice because they can exist as colloidal suspensions. We can have really large concentrations of them, so maybe in the tens of molar, and then they're really molecular-like. And in the end, I will stress a little bit why at least my group cares about this. If we think about a molecule in a microcavity, there are 2 things that I want to maybe bring your attention. The first one is that the molecule cavity interaction is happening predominantly in the center of the cavity. This is because this is where the antinode of the mode is. And the second thing is that once the photons leak out of the cavity, they are gone, and then we don't have to worry about them anymore. And these 2 points are different when we put molecules on plasmonic nanoparticles. To start with, these molecules are in direct contact with the cavity, the plasmonic cavity, to the point that they can not only exchange energy, but they can also exchange charge. And the second one is that when the plasmon mode leaks out, it can emit a photon into the far field, but it can also generate hot electron states. And these hot electron hole states are going to be also in contact with molecule and be able to interact with it. So in this case, this is the nanoparticle. I have one excitation that would correspond to the plasmon mode, and then I have a continuum of the conduction band that will also be excited. And in the talk, I will talk about 3 things. The first one is the experiments using 2-dimensional electronic spectroscopy to study the dynamics from beginning to end. And the second part will be on how we are starting to model these spectra. And then on the third one, just a bit of an outlook on the new systems that we're synthesizing in order to treat polaritons almost as a chemical functional. Okay, so I give a brief overview of what is known in ultrafast dynamics of molecules in microcavities, confining myself only to optical polarity, so in the visible. If we start from the very early times, in these maybe open cavities, people have seen oscillations that correspond to the rapid splitting of the strong coupling regime. also in these cavities, and as well as in fully closed cavities, people have seen that in general the energy cascades from the upper polariton into an exciton reservoir, and then from the exciton reservoir or the dark states, it goes to the lower polariton, and from there it decays to the ground state. There's also a pathway that can leak out that makes the excitation of the upper polariton radiate a photon and recombine to the ground state. Recently, work with 2D spectroscopy showed that there was also a transfer from the upper polariton state directly into the lower polariton state, and I will talk a little more about this later. And finally, some theoretical simulations have shown that you can have an equilibrium that is established. So even the lower polariton can go back to the dark states, and the dark states under some conditions can also repopulate the upper polariton. So this was only for optical polaritons. Actually, most of the work that we used to explain the measurements that I will show you came from Hoyle and Wei's work on 2D spectroscopy of molecules in IR cavities. So this was also very important, even though I will not mention the details here. So in summary, everything goes down, but there's somehow a thermal equilibrium that is established between the dark states and the polariton branches. The story is quite different when we talking about these plexcitons, these plasmon plus the excitonic states of CN in dyes. First of all, there are less studies, there is less microscopic information, and there is a large spread in lifetimes that I think is due because in some systems you have phenomena that is absent in others. So for example, in 2014, Balchi et al. With systems very similar to the ones that I'm going to show you, measured timescales for relaxation from between 2 to 15 picoseconds, and measured a relaxation from the upper branch to the lower branch. A group at Aragon measured a slightly different system, and they managed to measure a very, very long lifetime of 300 picoseconds, which they attributed to a charge transfer from the molecule to the metallic nanoparticle that would stabilize this energy as a charge transfer state. And then you have some other work that is very important, not because of the timescales that they report, but because they are focusing on the line shapes that one obtains when exciting these plexcitons. But we got interested because there was still maybe a bit of a gap and not enough studies to have as clear a picture as what was happening in molecules in microcavities. This is the experiment that we do. So for those that are not familiar, I will say in 30 seconds the essentials. So it's a time resolved method that consists of maybe 3 sections. The first one is a pair of pulses going to excite the system, and we use a pair of pulses because eventually this gives us energy resolution along the excitation dimension. Then we have a waiting time in which we can wait and take snapshots of the molecule so that we can see where the energy is going. And then we have a detection scheme. In this case, it's provided by a pulse, which leaves the system in a optical coherence, which then emits, and we detect it with heterodyne with a local oscillator to get phase information. In the end, we Fourier transform along 2 dimensions and we get this type of maps. So this is an example of a system with 3 predominant transitions, and in the diagonal something analogous to the populations, and then you can see all the couplings between the states. And this is the instrument that we use. This is in the lab of Donatas Sigmantas in Lund University.
Sorry, Professor.
Yes.
Your connection is a bit unstable. Maybe you could switch off your webcam.
Your camera, yes.
Thank you.
Should I repeat something or not?
I think it's all right, but sometimes it lags a little bit.
Okay, just 1 second. Okay, hopefully that is better. Thanks, Stefan. So this is one of the first examples of 2D spectroscopy on polaritons, where you can see that you have the diagonal levels and then you have the couplings connecting them. And then you can measure the dynamics. So this was in infrared cavities. It was recently done also in optical cavities. And in this case, this was what gave the clue that you had a decay from the upper polariton directly to the lower polariton. This is the system that I'm going to be telling you the most about. We have a very broad plasmon transition in blue that when we couple to the bright transition of these TDBC J aggregates, splits into a lower polariton and an upper polariton. And the expectation, at least that we had, is that we were going to have these diagonal peaks and the cross peaks connecting them. And in fact, the spectra turns out to be quite different. Maybe to complicate the problem, the bandwidth that we are able to access with our spectrometer is narrow. So in here, I show the absorption spectrum, and I show a very narrow laser spectrum. And this is not a problem. We're able to shift the spectrum around, and the results that I'm going to show you do not change significantly. To make things worse, not only do we have something that we still cannot recognize as an upper branch and a lower branch, but this thing shifts around with time. So there is some spectral diffusion, and there are some oscillations that are in addition attributed to we have an additional Raman modulation of the signal, which makes things more complicated. But so the goal is to understand what happens from the moment of excitation, understand all of these spectral diffusions until the moment where the excitation is thermalized. And for this, we analyze each individual component. So we remeasure stuff that was already known, but we remeasure it for our system, for the J aggregate, for the plexiton, and for the plasmon. And as you can see, the spectra is very different for the individual components. In this case, I show you these were maybe measurements that took 1 year to make and another year to understand. And this is the kinetic summary. For the J aggregates, it is known that after the dephasing, they are transferred to dark state very fast, within 80 femtoseconds. After which there is a longer decay timescale associated to exciton-exciton annihilation. And this happens with an energy dependence on the laser intensity. And then finally, we have a very long relaxation back to the ground state of a couple of nanoseconds. So in this case, I put more than a nanosecond because the time range of our instrument does not go beyond that. For the plasmons, we have a very different story. We have a very fast dephasing that is usually this generation of hot electron hole states. And then we have electron-electron scattering processes, electron-photon scattering. And then we are lucky enough to have something else, which is a ground state oscillation of the nanoparticle. So we have deposited so much energy inside the nanoparticle that we excite a breathing mode. And this breathing mode is actually a very, very clear indicator that the energy is dissipated inside the lattice. And this will be important to understand things later. So I'm just going to repeat it one last time because it's maybe not everyone is familiar with excited states in metals. So the first thing that happens is we excite the plasmon, so we polarize the metal, and then we have a very, very fast wave vector.
Professor,
yes?
we have a question.
Yes.
Okay. We have a question from Joel. Actually, Stefan, can you show me how to unmute them?
Yeah, I can do it.
Thanks.
Joel, you got the floor.
Hi, Daniel. Just sorry, very quick question. What is the frequency of the mode of the plasmon, the vibrational mode that you're talking about?
Oh, I think it's about 11 picoseconds.
Wait, sorry, compared to to wave numbers or something like, so can you just give me like an estimate so that I calibrate it to what I know about vibrations?
I think it's in the terahertz, I think,
Terahertz.
Or even a bit fractions of terahertz.
Okay.
So it's a very, very slow mode.
Okay, thank you.
Yes. Yes. Yeah, it's very, very, very slow, but it modulates the signal very, very clearly. Okay, so after this initial excitation of the plasmon, we randomize the wave vector, we excite a non-equilibrium distribution of electrons, and then usually there is this simplified version of a two-temperature model, but we have electron-electron scattering that thermalizes the electron temperature, and then we have electron-photon scattering that thermalizes the excitation back to the lattice, and then we have a hot nanoparticle. And because we've done this so fast, we excite this breathing mode. And each one of these processes has a clear spectral feature in the transient absorption. And so we use this in order to assign what is happening to the plexitons. So I will maybe elaborate more on this, but essentially, if you have a nanoparticle that you warm up, you will redshift the absorption, and in the transient absorption, it has this differential line shape. And the plexitons, this is the result. We have a dephasing that we measure from the line shape, followed by a very fast transfer to dark states, which are essentially molecular in this case. And then we recognize the processes that are happening inside the metal. So we have electron-electron scattering that is a little bit slower than in the metal without molecules. We have electron-phonon scattering that is a little bit also slower than the bare metal. And then notably, we have no vibrational mode. And so all of this picture is, maybe we came to it by self-consistently. So we have no energy dissipated inside the metal, or not enough to excite the mode, which means that it has to have dissipated elsewhere. And in this case, it's related to the molecular covering. Maybe I show, just repeat what I said. What we found is that we have first maybe some radiative recombination and an injection into dark states, followed by these many body processes inside the metal. And then we have lattice cooling. And something really surprising, and that is in contrast to polaritons in cavities, is that now the molecular dark states that are supposed to live a nanosecond don't survive past the electron-electron scattering time. And so what this means is that there is a short circuit between these molecular dark states that are even more insulated inside microcavities and the surface that maybe via some surface-induced process quenches the energy. So this is also very important. We've analyzed many systems with different coupling strengths. So this Sinan Balci made a series, or in his lab they made a series of these systems. In this case, in the orange is the data, and then we have a fit to the data, and we analyze this with 2D spectroscopy, and we see more or less the same picture, only some quantitative changes in the different scattering rates. So maybe we are not yet so confident in the scattering rates to immortalize them in a YouTube video, but let's say the picture is preserved even across samples, and these ones are no longer nanoprisms. They are just these donuts with a bit of silver, a little bit of gold, so it's an alloy, and then the J aggregates are in the center and around. So the conclusions for the experimental part is that the plexiton dynamics and the optical response necessarily has to be understood in terms of molecular and metallic many-body processes. Something really drastic is that even these molecular dark states are quenched on the time scale of electron-electron scattering. So it has two effects. On the one hand, it significantly shortens the lifetimes of the J aggregates. And on the other, it increases, let's say, the lifetime of these hot electron distributions. And this is actually important because there's a lot of chemistry that is driven by hot electrons inside metals. And so we want to explore whether this is something that we could use to drive reactions more efficiently. But we haven't done that experiment yet. It's in the works. Okay, so the next part is to understand a bit.
Excuse me.
Yes.
Sorry, we have two questions.
Yes.
Joel, go ahead.
Okay, Daniel, I find this observation quite interesting. So let me just ask you the first question. So you said that the terahertz mode is not activated in the plexiton, and you ascribe that to essentially relaxation faster to the dark states than to the plasmon. But for example, wouldn't, if the temperature goes down, if you lower the temperature enough, transfer to those dark states could be quenched, and therefore you could recover the oscillation of the terahertz mode? Could that be possible?
You mean doing the experiment at nitrogen temperatures, for example?
Yes, so that you suppress the transfer to the dark states, for instance. Do you think that would like resuscitate the oscillations of the terahertz mode?
Yes, I think if we suppress the transfer to dark states, then yes, I think we have to recover at least to some degree, this oscillation. So we have tried doing experiments, in particular with pump probe, where we take the plexcitons and we slowly start to increase the intensity. And at some point, we recover the oscillation. But, but it's not clear if it's because we have managed to put more energy in the mode or because we have damaged a little bit the sample. But we can recover it only by increasing the intensity of the pulse.
But then the others, but I don't think I understand the statement that you make at the end in your conclusions. Can you go to the conclusion slide where you say that that the dark states increase the lifetime of the hot electron distribution? Is it because you have like a steady source of energy? Yes. Okay.
I think so. So instead of feeding the energy of the dark states into, for example, a lower polariton, then you just end up feeding it to the electrons in the metal. It's not very correct language, because I think even some people would disagree that you have an electron time scale. So this is still a very simplified model, but the idea is you are feeding the energy directly into the electrons of the conduction band of the silver.
I see. Okay, and then sorry, one very quick question. So how likely is it that due to inhomogeneities of the J aggregate, just because of inhomogeneous broadening, you quench the oscillations of the nanoparticle and therefore you don't see them? Like, is that a possibility?
Yes, you mean the only way that I think that this could work is if you are absorbing, if you're somehow damping the vibration much faster because you have something molecular on top. But I don't know. Of course, we can't rule it out. But again, increasing the intensity of the laser, we still recover the oscillation with very similar damping time. So it seems like the problem is that you don't put enough energy, not that you're modifying the mode by the molecular covering.
Okay, thank you very much.
Arkady?
Yeah, can you hear me?
Yes.
Okay, so yeah, I have a question about that Raman modulation that you were talking about. So is the cause of that something like, so it's basically a low frequency mode coupled to high frequency mode, right? So the cause of the Raman modulation is it like more prominent because the electric field is very strong? Because like the second, so for electric field which is small, I wouldn't expect that kind of a Raman modulation, right? Because it's a form of like E dot x square kind of a term, is it?
It's I didn't get the last part. It is
so it's a second order process, right? So if the electric field is weak, then that modulation won't be there, is it? So it's because just because it's a plasmonic mode, so we need to consider that is important, is it?
Yes, you are correct. So in general, you can always have modulations of vibrations in the ground state because your laser envelope is broad enough, so you can still excite it. I guess it would be along the ground state bleach, but it becomes very, very strong because the field is enhanced by the nanoparticle, and you get exactly the same modes that are enhanced if you were to measure a normal source spectrum.
I see. Okay. Thank you.
Yes, it's actually a little bit annoying because it covers. I think it would cover any possible electronic optical oscillation since it is so strong.
Yeah.
Okay, so for the second part, I want to talk a little bit as to on how we simulate these experiments. And the picture that we have is at least we start from a molecular partition coupled to a metallic partition in which we are including the conduction band and then plasmon transition. And maybe there are many ways that you can treat this, and many people have done it in the past, and you arrive at an effective Hamiltonian that only includes the right modes and which has non-Hermitian terms. So what one gets in this Hamiltonian, we have the ground state that in this case is predominantly coupled to the plasmon, and this plasmon now has coherence, and this plasmon mode is coupled to the J aggregate, and this also has some non-Hermitian term that corresponds to the coherence. Alternatively, you can also partition the bright state and the dark state and use projection operators, and you will get the same thing. But if you do it in this way, you can also justify the use of the non-Hermitian operator in response function. So the way we simulate this to the spectra is we select the third order response. So this is the convolution of the electric fields that we are imposing with the experiment. And this commutator of commutators is the response function. We take, for example, the first term, which is just the product of transition dipole moments. We can project everything out onto the bright state, and with some plastic approximations, we can just justify that this is just the evolution of a system with a non-Hermitian effective Hamiltonian. The general case, if we don't do this wide band approximation, is more complicated. We start to have non-Markovian effects. We actually start to have density matrices that don't have the traces not preserved, but we haven't gotten to that point yet. And so if we have now the same, we can use the same formalism that we would use for molecular transitions for spectroscopy on chromophores. Then we can just put the 3 pulses into the electric field, and we can calculate the usual response functions for 2D spectroscopy. And of course, we can calculate the 2D spectra, but we can also calculate the linear response. And in this case, the green is the experiment, the magenta is the simulations, which I think are quite good considering the simplicity of the model and the complexity of the real system. And then just as a reference, if we were to use a Hermitian Hamiltonian, then we would have a fit that doesn't really reproduce the line shape. Okay, and this is very analogous to what other people have used, such as coupled oscillators or Lindblad terms with local baths. And we can use the same thing with third order response. So we need to introduce a nonlinearity, and in this case, we just use the one that Rivero et al. From Wei and Huel's work used, and it's a Rabi contraction where the molecules that have been excited no longer participate in the Rabi splitting, and this corresponds to these Feynman diagrams, and then we get a good agreement between the experiment and the theory. And we can also justify the hot lattice in a very simple way. We consider that the nanoparticle warms up, it expands, and this increases the volume. The number of conduction electrons stays the same, so the plasma frequency goes down, and we at least qualitatively reproduce the data. And this is very important because it means that the last spectrum that we can measure does correspond to a hot plexiton, and this means that the last process is likely an electron phonon scattering and so on. So it's just one more sanity check. I mentioned that we have a very narrow bandwidth compared to the extremely large bandwidth of the plexiton, and this is just to give you a scale. Let's say the full spectrum is the entire spectrum of plexitons, and this is what we were able to measure. So this is in the early time simulation, and this is in the late time simulation. We did check that the model was working for other bandwidth by doing pump probe. So this is another plexiton system where we have this Rabi contraction with the data and the fit, and it works quite well. And we also measure it at late times. And in this case, there are some regions that don't fit so well, but I think it's reasonable. Maybe to go a bit further than just explaining the experiments, we can do a systematic exploration of this nonlinear and linear spectroscopy of non-Hermitian Hamiltonians. And in particular, what I want to show you is how we can decompose the signal into individual Feynman diagram contributions, maybe examine the symmetries of the signal and analyze the changes above and below the exceptional point. So this was, this has been known for a very long time, and it was discussed by Said Rodriguez in the context of strong coupling, that this non-Hermitian Hamiltonian, whenever the plasmon transition and the molecular transition are as isoenergetic, it admits an exceptional point. So this means if we take the real part of the eigenvalue, so the energy of the polaritonic states, we have, let's say, no splitting until we reach the strong coupling condition, and then we see the Rabi splitting. The opposite happens in the dissipation. We're going to have polaritonic states that have a different dissipation until we reach the strong coupling, and then both branches will have the same dissipation. And if we look at the spectra above and below the exceptional point, they look a little bit different, but still they are quite similar, and they become even more similar the more we approach the exceptional point. Let's see. The eigenvectors are the eigenvectors are shown here just for completion. So we have the upper branch that is only a half and half mixture of plasmon and molecule after the exceptional point, and below the exceptional point it's not half and half. So what we can analyze is how the linear and nonlinear response looks like for different regimes, and we take this some classification by Pelton in terms of the coupling strength normalized by the transition frequency of the emitter, and also the dissipation also normalized by the transition of the emitter, and we select these points. So just to illustrate a little bit more, the green is supposed to be a weak coupling regime. The orange is something called the cooperativity regime, where we have very important interferences processes happening. And then when we are all the way here, we have the strong coupling regime, and this is what the line shapes look like. I'm going to be just in the next 4 or 5 slides using these diagrams a lot. So we have, when I'm writing this red arrow here, it means that I consider that the J aggregate couples predominantly to the dark field. And when it's blue, it means that it's the plasmon that couples predominantly to the dark field. And even though the energy of the branches is exactly the same, the spectra can be very, very different, depending on which one is coupling to the far field. And in particular, we see, let's say, a splitting of the peaks or a dip almost always whenever the plasmon is coupling to the far field. And we can make this a little bit more clear by decomposing the signal into the individual Feynman diagrams. So in this case, I have again plasmon coupling to the far field and then generate coupling to the far field. This clock is the transition dipole moment in the complex plane. And then you can see that, in fact, each polariton branch is contributing to a different peak in the spectrum, whether we are in this first case or in this second case. And when we go to the weak coupling regime, things change. So first of all, when it's the molecule that couples to the far field, we can see that the spectrum broadens, but nothing more. And when we're considering the plasmon coupling to the far field, we have an interference dip. And so because of the non-hermeticity of the Hamiltonian, we have this a negative contribution. And this illustrates, I think, very well the difference between Rabi splitting and interference dip. Okay. Sometimes I just make a quick aside. Sometimes people will invoke toy models, and the 2 toy models that are most used for this type of behavior is a lambda system and a Fano system. And the idea is that whenever, at least whenever for a lambda system, you don't have this transition, you will have an electromagnetically induced transparency or an exciton induced transparency, where if you have coupling of 2 lower levels to a higher state, there will be a destructive interference and you will not populate these levels. And the same thing happens with a Fano model. And there's a reason why I'm saying all of this that will be apparent in a couple of slides. So just to elaborate a little bit, for Fano interferences, we have 2 paths to reach this heterogeneous distribution of modes, this continuum, and this creates 2 things: a point of destructive interference, and it also creates an asymmetry in the profile, and this is clearly seen here, and this asymmetry is given by the ratio of the strength of the 2 pathways. So we can rearrange our exciton to be able to conform to this picture. So we just readjust this a little bit. This is an effective ground state, even though it's the excited state of the molecules. And then if we look at the spectra, we see that, in fact, at the point of destructive interference, they are the same, and this can be proven mathematically, and elsewhere they are not. And this is very drastically seen when we start to consider more realistic cases for the plexcitons. In this case, we have the lambda system, and as we start to increase the coupling of the molecules to the far field, so I didn't say it explicitly, but in our system, it's almost exclusively the plasmon that couples to the far field. And the molecular transition is about 5%. The transition dipole moment of the right state is about 5% to that of the plasma. As we start to increase it, we start to lose this contrast in opposition to the Fano model, where the only thing that we're doing is shifting around the minimum. And not only do we shift it around, but we can make it change sign depending on the sign of the asymmetry factor. So this is something different. And now I want to show how we can actually recover these phase shifts by looking at the nonlinear response signal. So what I'm going to do is I'm going to take only one of the contributions from to the spectra, and this is just to make it a bit clearer, but they all follow the same idea, and analyze it under weak and strong coupling regimes. So the first thing that we see, in this case, we have kind of a clover shape, which is then become more apparent. And the moment that we skip to the strong coupling regime, the signal changes also qualitatively. So we go from this maybe twofold reflection symmetry to this 180-degree rotation symmetry. And so, whereas in the linear response, we don't have so much of a qualitative difference, the nonlinear response does have a very, very strong indicator that we are in the strong coupling regime. Moreover, we can also look at what happens when both the plasmon and the J aggregate couple to the far field. And then in this case, we can recover the asymmetry. So in this case, along this dimension, you will see that you have recovered the asymmetry that was present in Fano systems, but not in lambda systems. So is this important? Well, first of all, it gives some intuition and some insight as to the processes that are happening in plexcitons. But also, if you happen to measure these asymmetries, then you can understand the model a little bit better. Maybe just one thing I want to mention is that you can do a decomposition of the interference signal into the individual components. So we have two excited states, plasmon and bright mode. So, and we can, upper polariton and lower polariton. And so we will have 4 diagrams, and these are shown here. The diagonals are positive, and then we can clearly see that the cross peaks are going to give the interference that gives this final clover-like signal. And then again, maybe a bit more clearly, if we project 2D signal along the detection axis, we can start to recover asymmetries depending on the relative sign of the transition dipole moments. Okay. Maybe I want to mention one thing along the same lines, that this would be one way in which we can distinguish experimentally whether we are in the strong coupling regime or in the weak coupling regime. And there's some work also by Pelton where by measuring scattering and measure photoluminescence, this becomes very apparent. So in the weak coupling regime, there's only one single both scattering signal and then photoluminescence signal. When we go to the splitting, we can see the splitting both in the scattering and the photoluminescence. And when we are in this interference let's say medium coupling strength, then we can see that the splitting is not very apparent in the photoluminescence. And so this is another way in which you can tell, and this is something which translates into a real measurable signal and measurable physics. Well, for the conclusion, yes,
we have a question.
Yes,
Joel, go ahead.
Sorry, concerning the last panel on the right-hand side, my understanding is that with like microcavities, the PL, okay, I guess here the PL, is it coming through the dipole of the plasmon when you calculate it?
Yes.
Okay, so. Because when it comes from the molecular side, my understanding is that you never see the upper polariton photoluminescence. So then, because everything is dominated by dark state filtered through the lower polariton. So could you comment on this? Like, if there are dark states, do you also expect the upper polariton to partake in PL?
No, I also agree. I have seen, I think, okay, this is a theory, but there's also experiments. And in the experiments, I think they also see the photoluminescence from both branches. But from the experiments I have seen, I think the dark states play a really big role. And if I remember right, in this case, they have some type of nanocube or nanoparticle. It's here, nanoparticle sitting on top of a silver surface. And I think the dark states are a lot less than what you would have in a microcavity with I don't know, thousands of dark states. In this case, there are not so many.
So these are also very similar to the architectures you use, like the plexcitons you fabricate?
No, I think in our case we have a very large number of dark modes, but in our system I haven't measured photoluminescence yet, and in these particular states they are quenched really fast. So after 2 picoseconds, you don't see anything. I mean, there's no longer an electronically excited state.
Thank you. Yeah.
But yes, I think you're right. In this case, it's basically limited to the cases where you have almost single molecule limit, because otherwise the dark states they are overwhelming the.
But even in that case, what I'm confused is, like, if I believe in Kasha's rule, wouldn't I believe that everything relaxes to the bottom of some excited band and then it emits?
Yes, I don't know if the plasmon plays a role, and it's very fast. I mean, there are some instances in which you can violate Kasha's rule, and I don't know if this is one of them. We've thought about analyzing this also with time resolved methods and doing time resolved photoluminescence for the plexcitons that I'm showing, but they don't have such a strong signal that we can do it. So we haven't managed yet. But it's something that we're interested in, exactly because of what you're saying, that many systems show different things, and we want to see what these plexcitons are doing, but we haven't done it yet.
Sounds good. Thank you.
So in the conclusions of this theory part, we have that non-Hermitian Hamiltonians and double-sided Feynman diagrams reproduce the data very well. And in addition, they provide this useful decomposition that makes interference processes very clear. And then finally, there is, I think, maybe once we learn how to do broadband 2D spectroscopy, I think there's a big role to be played in just characterizing even the structure of the systems, because there are certain things that become apparent when we consider the third order response, such as asymmetries and some symmetries in the spectrum. So then maybe for the last 5 minutes, I want to give a bit an outlook on what my group is currently doing and how I think that these systems can be interesting. Mainly because they are definitely not extending the lifetime of the molecules as they are, but I think perhaps this doesn't have to be a bad thing. And so right now, what we're doing experimentally is pushing for stronger coupling. So we want to find systems that are, let's say, unambiguously in the strong coupling regime to see how the dynamics are changing. We are currently working on doing some more complete modeling. So at the moment, with what we have, we can simulate the very early times or the very late times, but we need to understand everything in between. So all of this spectral diffusion caused by this electron-electron scattering. And then we're also moving towards trying to do, even if piecewise, some type of broadband spectroscopy. So we have started to do some experiments where we shift the laser frequency around, where we do 2-color experiments, but these are really, really difficult to do. And it's very, very difficult to piece everything together, especially for plasmons, because they seem to change a little bit the response depending on what wavelength you are irradiating them with. And then the last step where I think maybe this has a role that can be explored more is in photocatalysis. So for molecules in cavities, there's, I think, an unending list of things where they have been useful and they will be useful. So this energy level engineering or remote energy transfer, accelerating reaction rates, and doing non-equilibrium condensates and lasing. And for the emitters on plasmons, I think there's also a lot of things that has been explored only on plasmons by themselves. So there is hot electron photocatalysis it can drive a large number of reactions, and it can do it relatively efficiently. Also considering the lifetime of the excitations, you can also have some interesting charge transfer processes happening between metal and semiconductor. And then recently, I think this paper is maybe 2 or 3 days old, you have some interesting catalysis that can happen with these nanocubes on surfaces. So whatever you're doing on the metal can be very useful for doing chemical transformations as well. And one of the things that we want to push is that taking advantage that these plexcitons are colloidal in solution to try and think of them as a functional group. So you have a molecule and you want to affect its reactivity, and you just start putting different functional groups. And the idea is to do the same thing here, except that polaritons are much bigger. So in this case, you need to consider bigger systems. And this can be also very interesting, especially for solar energy. So on the left or on the right, I show some systems that can photoreduce protons into hydrogen, or that can split water into oxygen. And they are conformed of several nanoparticles, a lot of chromophores. And one of the things that would be interesting to see is whether you can replace some of these groups by polaritonic states and ask what can be accomplished with that. So it's a very complicated problem because you have also very complicated architecture. So in my group, we've started to do organize a little bit these arrangements, and so far we have started to do something that is a very old problem. How many spheres can you tightly pack around the center one? And we try to do these Newton's kissing spheres with gold nanoparticles and titanium dioxide nanoparticles. And so far, I mean, we are getting there. So we have colloidal systems that can respond to light. So we see red shifts when we start to put gold molecules around, and the next step would be to try and put some J aggregates and measure polaritonic states then coupled between semiconductors and metals. So this is something that my students are currently doing. And so maybe to have a conclusion, I think when we first started this topic, we were thinking that we would do quantum optics in a beaker. And in the end, it's very, very hard to reach strong coupling limits, at least unambiguously, and then be able to have systems that can withstand this ultra-fast spectroscopy. And it turns out that we have more, not so much quantum optics, but atomic physics in a beaker. So if we have these nanoparticle arrangements with a lot of molecules and some conduction bands, this looks very similar to what, for example, the helium energy spectra looks like, where the continua are photoionized states. And so it's more trying to connect the two. And we've also started to do it with some collaborations with attosecond spectroscopy people, with, for example, the group of Annullier in Lund and Andreas Buchleitner in Freiburg. And so now we're going to try and pursue this type of arrangement, thinking about this photocatalyst with lots of semiconductors and lots of metals and lots of molecules. And so with this, I just want to say again the people that participated in the work. Pierre Adriamont, who is an expert in phonon modes, Semana Saisonen and Professor Balci's group that synthesized the nanoparticles, and Lucas Wittenbecker, Julia Minda, that with whom I did the spectroscopy, and Panu Puleritz for the theory, and Donata Sigmantas for his instrument. And thank you for your attention.
Okay, thank you very much, Professor Finkelstein. It was a very interesting talk. So now we will open the floor for questions. So is there any question from the audience? I have one question for myself, maybe. So in your model for the dissipative dynamics of the plexcitons, you approximate the dissipation using a non-Hermitian Hamiltonian. Could you summarize what are the criteria I need to take into account if I want to choose between using a full Lindbladian dissipator, for instance, and or approximated using a non-Hermitian Hamiltonian? What are the most important things?
I think it's the same as long as you stay in the weak coupling limit with the field. So since we're doing a perturbative expansion in the field, so with this response function, then it's the same because this term in the Lindblad that returns you to the ground state is not in the order that you're considering, and so you don't consider any saturation effects. I think for us, in terms of looking at 2D spectroscopy, the typical approach is to just go to an excitonic basis and then include some dephasing there, which then gives you a broadening of your polaritonic states. In this case, this is not what we're doing. You're doing a broadening of the sites and then you're coupling them. And so this turns out to look very different in the spectrum.
Okay, and there is no, the evolution of the coherence between the two states is irrelevant in this case, right? Because you have most of the population in the ground state.
And no, I don't think it's irrelevant. I didn't understand.
In the Lindbladian, you have the phase damping terms, right? That they will decrease the coherence maybe at a different rate than the populations. And in the case of a non-Hermitian Hamiltonian, it's only the population terms that are accounted for. So maybe, do you think it would have any particular effects, or is the time scale just similar for the decoherence with respect to the de-excitation?
Yes, I think you also I mean, this non-Hermitian term also you relax the populations, but then you have this population induced you relax the decoherence because you relax the excited state. The only thing you can do is keep your excited state and relax the decoherence in this non-Hermitian Hamiltonian. So I can tell you the direction that we're going at the moment is if you consider the structure of the conduction band, for example, or same thing with the molecular dark states, but it's more obvious with the conduction band, then you will have some maybe non-Markovian effects where you have the population that can come back. And in this case, it becomes a much more complicated problem where you have non-linear effective Hamiltonian. So we're starting to do that. So you would have examples where your plasmon goes to the conduction band, your excitation goes to the conduction band, you lose some population, and at some point it can come back, for example, into dark states. And this is possible physically because everything is close to each other.
Thank you. We have another question from Matt. Matt, you can go ahead.
Hi, I have a question about the modeling regarding where you showed the interferences, like how you showed the dependence of the spectra on the sign of the transition dipole moments of the plasmons and the aggregates, as well as, like the phase for the phono interference. So I was wondering, in your experiments, how controllable are these parameters? Like so like in the next slide.
The next slide. This one?
Sorry, one or two more. The one where you have you show both the phono resonance and then the.
Okay. No, I don't think. I mean,
yeah, this one. So like, how controllable are these parameters in your experiments?
No, in our experiment, they are not at all controllable. I mean, or only one is controllable. You can change the coupling strength by adding or removing molecules. For plexcitons, this is the relevant model where you have this three-level system, and then what you get is a decrease in the contrast when your molecule is absorbing. But you can't control this. It's more an exercise to be able to read what is happening with your system. And maybe it sounds, maybe it's not trivial, but maybe it sounds very simple at the moment because we only have one molecule. But our ambition is to, I mean, you have this nanoparticle and you keep adding molecules and you keep adding different structures of the monolayer, and maybe you want to add some different type of molecules, maybe two cyanine dyes. And in this case, then you need to be able to read the spectrum a little bit more subtly. Yeah, it's a bit more to see what information you can get out. But we are not controlling this at the moment, other than the coupling strength.
I see. So it's just a way to, like, at least it's a phenomenology, right? To interpret
exactly
to some extent what's going on. Okay. Thanks.